Okay. So good afternoon, everybody, and thanks for staying until the very last bit of the day. And of course, let me start by thanking all the organizers of this program, also Dynamical, for setting up the program, and of course also for giving me some time to discuss some topics here with you in this first week. So for those of you with whom I did not have a chance to talk to yet, so let me introduce myself. My name is Valentina, and I'm member of a lab which is called LPTMS, that is right above us, so in the two corridors on top of this room. And what I'd like to do in here today and tomorrow is, in some sense, a prosecution of the course that was given by, yes, it's a bit weird. Here it's better. Yes. Okay. Okay, so let's see. If you don't hear, please let me know. So this year is going to be a prosecution of the course that was given on Monday and Wednesday by Laura. So that was essentially about this scenario for thermalization of isolated quantum system, which goes through this eigenstate thermalization hypothesis. But the idea in here will be to somehow talk about very similar things, but from the opposite perspective, if you will, which is the negative view on ETH. So we will be interested in discussing cases in which this ETH is actually violated. And it does not. So let me, before going into what is the outline, I just wanted to make a comment. So the idea or the way I thought about this is rather than taking maybe one particular example of systems violating ETH and discussing it in detail, I wanted to instead mention a few things that have been discussed in recent literature that are maybe a bit different from the others, with the idea of, especially for those among you that maybe don't work directly on these things, of giving some terminology that may be useful for discussions in the coming weeks during the program. So this is not, let's say, conceived for experts of these topics, but I see that there are experts here, so they should not leave, but they should somehow make comments and integrate what I'm going to say. If this becomes a discussion, it would be also very important. Okay, so the idea of the things that I like to discuss is given here. So this is following my slide. So as Laura told you, the question that you're interested in is how to, let's say, merge ideas coming from quantum mechanics. So dynamical, they don't hear online or here. Maybe I should keep it like this. No, the blue one, I think it's really just for online people. Okay, let's try this. So the basic question behind all this is how to, let's say, merge these ideas of quantum dynamics with statistical mechanics. So with the emergence of thermodynamics and, let's say, Gibbs-Boltzmann type measures. And what are possible exceptions to this? So Laura explained very carefully that this question can be translated in terms of properties. So if you think about unitary dynamics, you can relate or justify the emergence of statistical physics ansatz on the structure of the eigenstates of the Hamiltonian that governs the dynamics, and this is precisely the idea of ETH. So when you ask about exceptions to thermalization, this is very naturally phrased in terms of breakdown of ETH. And as you see, there has been a lot of, let's say, work, in particular in recent years, on figuring out what are possible mechanisms that produce such a breakdown of eigenstate thermalization. And these are just some keywords that I would like to touch upon in the following, let's say, 2 hours. And this will be the first part. And then in the second part, since after all this, the program about
quantum chaos, I would like to make some connections with ideas or concepts that, that are standard or that have been investigated a lot in this literature of quantum chaos. And in some sense, this is maybe more related rather than to structure of eigenstates to properties of the spectrum. So the distribution of energy levels of the Hamiltonians governing the dynamics. And so in here, what I'd like to do is first of all to discuss or to recall, because actually this emerged already in some of the previous lectures, what are possible diagnostics of quantum chaos that you can look at by studying spectral properties of these Hamiltonians and how they have been used and let's say looked at in contexts in which this ETH breaks down. And I will try to do this thinking in particular about problems of localization. Then I'd like to say just a few words about ideas which come from maybe the field of quantum glasses, and that in my view are related, even though quite loosely, to billiards. So how to think about problems of billiards, but in a very different context, which is very high dimensional. That is what people in quantum glasses tend to do. And finally, if there is some time, I would like to go back to this concept of quantum scars and comment about the emergence of periodic orbits in connection to, indeed, to this phenomenon of quantum scars, which may not be, let's say, the connection may not seem so trivial at first, but there are works, in particular recent work, which suggests that if you define some sort of effective dynamics of your system, you have, in fact, periodic orbits which emerge also for this type of quantum systems. So this second part is a bit, let's say, self-made selection of topics. So this is by no means exhaustive, and I think there are many more connections that will emerge also in the course of the following weeks. But for time reason, I will try to focus on these three. Okay, so this is the somehow the outline. And now let me go to introducing what is, or recalling what is the main question in here. This is again related to what Laura told you. So the idea is that you know that, okay, this is going to be hard. So let me try again. So, yeah, but it was very noisy because. Sorry about this. Better works? No? It's a no? It's a... I'll try. Too hard. Okay, so what is the question? So what people say is that when you think about some generic quantum system, then you have such a system which evolves with its own quantum unitary dynamics. And you find that if you look at the system in some large time limit, then usually you see some thermodynamics which emerges, and you can in fact use thermal measures to describe what's going on in this large time limit. And this is a fate, so the fate of thermalization, which seems actually very robust for this quantum system, so which happens for generic quantum systems. And the question here is, what does generic quantum system means? So what are the boundaries for this type of universal behavior, if you want? And of course, if you want to understand the boundaries, it is very useful to understand what are exceptions to this behavior, so loopholes and violations of this scenario. Now, to introduce why this may be interesting, also a theoretical point of view, I like to borrow this sentence, which is taken from a paper of a few years ago. So this is by Serbin, Abanin, and Papic, and I think some of the authors will be here in the following weeks in the program. And in this paper, at a certain point, they formulate this question, which is, so they wonder what makes one particular initial state find its way back in the enormous Hilbert space, which is the Hilbert space of a 51 atom experimental system. That is an Hilbert space which has a dimension of the order of 10 to the 10th. So the question is, you have such a system, many body system, many atoms, or order of 50 atoms. you have a huge Hilbert space that is accessible to this system. You look at unitary dynamics and you find that starting from certain initial condition, the system somehow does not explore all this huge Hilbert space, as you may expect it to do. But rather, it looks as if it maybe goes away, but then it tends to come back to the initial condition at least several times during time evolution. And this is something that is intriguing. So it's something that you would like to understand, let's say, why it happens. So what do they have in mind when they write such a question? So what they have in mind is an experiment that was already mentioned, I think, in previous lectures, which was published in 2017. That is an experiment which was made by people in Harvard with a system of Rydberg atoms. So I'll not go into the physics of Rydberg atoms here, but let's say for the purpose of this sketchy discussion, for me, a Rydberg atom is essentially a two-level system. So it's an atom which can stay in two states. One which is not excited, which is what I denote with this, let's say, empty dot, and one which is the Rydberg state, which you can think of an excited state. So it's like a spin up and down. And what they're doing here is to take a bunch of these atoms, so of the order of 50 indeed, and to organize them into some chain. So they have a linear geometry. These atoms interact with each other, and this is encoded in this term here of the Hamiltonian that I will keep generic for the moment. So the N operator here is just a projection that counts whether the atom is in the excited state. And then you have this single atom Hamiltonian where there is again a term that contributes when you are in the excited state, and there is this sigma x, which just describes transitions between let's say the unexcited and the excited state, which are associated to this energy scale capital omega. Now, what do they do? So what they do is to probe the dynamics of the system with essentially a quantum quench. So this means that they prepare an initial condition that is of this form, so which has this very ordered local structure where you alternate atoms which are excited and atoms which are not excited with a period of 2. And then they change some parameter of the Hamiltonian here. So I think that they just switch off this delta coupling in here, and they let this initial condition evolve with unitary dynamics given by this modified Hamiltonian. And now what you would expect in general is that this unitary dynamics is such that very rapidly your system kind of forgets this detailed structure, ordered structure in the initial condition. So this, let's say, order is rapidly washed out, and you basically lose information on these alternating periodic features that you have encoded in the initial state, which is in fact what happens for this system if you start from, let's say, initial states which are not precisely this particular one. But you do start with this particular initial state. What you find is that the dynamics is quite different. So it is represented in this data here. So what they are showing in here is time versus a quantity that is the density of domain walls. So domain walls in here means, so a domain wall is essentially a pair of consecutive sites where the state of the atom is the same. So they are either both excited or both not excited. And what you see, so your expectation would be that you start with a very low density of domain walls, and then over timescales that are essentially related to some of the couplings, the inverse coupling in this Hamiltonian, so perhaps over times which are of the order of 1 over this omega, you lose this structure, and you have the number of domain walls which starts increasing in your dynamics. And this is indeed what happens in the first part of the dynamics. But then what you see is that once you reach this state, you then start going back, and you have all these oscillations which go on for timescales which are much larger than this 1 over omega, and which you can interpret as some manifestation of many body quantum revivals. So this corresponds precisely to this picture that is hinted at in the sentence before. So it really looks as if you start from the initial condition, you move away from it, but then you go back several times to states which are very close to the initial condition. So you see the revival is not perfect here. You have an envelope which decreases, and this is something that you can understand from theory for this particular model. But nevertheless, over these timescales, you do see that revivals occur, and this is really a quantum many-body phenomenon that you are looking at. So the question is, why is this happening? And why is this happening if you start your dynamics from this particular initial state? And as we will see, this is related to one of the keywords that I mentioned before, which is that of quantum scars. Now, of course, no, I think so. Even if you, so the way you understand this is you can go through writing an effective model which assumes that you have perfect blockade, which is this PXP model is a kinetic constraint. And then you would still have these not perfect revivals because the scars in these systems are not perfect and not exact. So it's not really that. It's really, even in the toy model with perfect blockade, you would still have this phenomenology here. But you can cook up models for which instead the revivals would be perfect, at least in theory. Okay, so let me show you another picture, which was already shown as well in some previous lectures, which is, if you want, the disorder counterpart of this experiment. So this was made a few years before in the group in Munich with cold atoms, in this case, in optical lattices. So in this case, what you're implementing is an Hamiltonian of particles that is not too different with respect to the previous one. So you see you have this term here is the kinetic energy. So these are fermions which can move in your lattice, jumping between nearest neighbors. You still have your interaction term in here, but the single site Hamiltonian is now different. And it is different because you have a potential at each side of your lattice that is not homogeneous anymore, but which is actually very, let's say, fluctuating in space, very inhomogeneous, and that you can reasonably think about modeling in terms of random variables. So it's not that you have, let's say, some sort of regular periodic potential, but these numbers are really regular, and the way you think about this model is as a model implementing an Hamiltonian with quench disorder, if you want. And what you do for this system is exactly the same as before. So you can again start with an initial condition that is structured and ordered. So you put, for example, fermions only in the odd sides of your lattice, and you let the even sides empty. So you now have a waving density of your particles. You run your unitary evolution, and again, what you would expect for a thermalizing system is that the dynamics is such that you, again, quite rapidly lose memory of this structure. And in particular, you would expect that the density of particles will reach some sort of homogeneous configuration in your lattice. Now, how can you measure this? So what they do in this experiment is to look at this quantity, which is the imbalance. That is essentially just the difference in density between the density that you have in the odd side and the density in the even sides. So this is what measures the type of order that you have in the initial condition. And indeed, it is a quantity that is exactly equal to 1 in your initial condition. And for a thermalizing system, you would expect that this quantity decays very fast to 0 during the dynamics. That is, in fact, what happens for this darker curve that corresponds to a capital delta here that is equal to 0. So if you switch off the disorder, everything happens as you expect it to happen. But then what you see is that if you switch on this disorder term, this imbalance quantity reaches some sort of stationary state, but the value of this plateau is different from 0, and it is actually larger and larger as you make the disorder stronger and stronger, which is telling you that the state that you reach in this relatively long time limit is actually not too far from the initial condition. So you do have memory of this initial condition, which is preserved in the dynamics of your system. And this is a bit different from the previous picture. So if you want, the idea here is not that you move away and you go back, but it's rather that you start from an initial condition and you stay more or less localized during the dynamics in the vicinity of this initial condition in the underlying Hilbert space. And as we will see, this is more connected to concepts like many-body localization, which are induced by the fact that you have disorder in your system. Okay, so this is to say that, in fact, there are loops to this scenario of equilibration and thermalization. And these loopholes, you can even probe them nowadays in experiment. And this is interesting, well, from the theoretical point of view, which is more the perspective that I will take. But it is also interesting for more practical purposes. So there is a lot of excitement in these communities because you are interested in probing features of coherent quantum dynamics in this many-body quantum system. So in view of possible applications for quantum devices and even quantum computing or let's say quantum devices. Okay, so this is just to give an idea of the fact that there is a lot of research, of course, going on in that direction. Okay, so from my point of view, which is more theory related, I think that these are all examples interesting because when you ask about non-thermalizing system, there is some richness which emerges in there, which is due to the fact that you can have different mechanisms that produce such violation of such universality. So I tried to state this by borrowing this very famous quote of Tolstoy. So the idea of a thermalizing system is that they more or less, at least in the long time limit, they are more or less alike. So this is why thermodynamics is useful. But when you think about non-thermalizing system, each non-thermalizing system is non-thermalizing in its own way, meaning that the mechanism behind, as I was saying, can be actually quite different. So in the examples that I'd like to mention, this will go from probing, let's say, tails of the distributions of observables, so mechanisms related to large deviations, to having effectively kinetic constraints in the dynamics of your systems that affect unitary evolution, to having conservation laws, which you can have both in clean systems or in systems with quench disorder, to having some interesting interplay between quantum fluctuations and underlying classical problems, which are complex in the sense that, let's say, the energy landscape without quantum fluctuations is already, let's say, is already interesting, and this produces interesting dynamics when you add quantumness on top of these problems. Okay, so this is again a summary of the different things that I'd like to touch. But before, let me just summarize briefly what is the setting that is in common to all of this problem and what is precisely what we are looking for. So how do you define a system which is not thermalizing? Which is, of course, which will be a negative rephrasing of what Laura has been telling you in the previous lectures. So the setting is as follows. So you're obviously interested in isolated quantum systems. So these are systems which are not coupled to degrees of freedom that you can model as some external path. Also, I will assume that there is no driving. So there is no open system, no Lindblad, as we have been seeing in the previous lectures. But you have unitary dynamics. So unitary dynamics means that you just have the Hamiltonian of your system, which generates time evolution. And you look at these dynamics starting from an initial condition that is a pure state in Hilbert space, and which you want to be somehow far from a thermal state because you want to probe that you reach a thermal description in the large time limit. So you start from an initial condition that is out of equilibrium. And usually this is taken to be some state in the space of your Hamiltonian, which are also the states that you can realize experimentally. So the examples given before are precisely of this form. So you look at quantum dynamics, but nevertheless, you put yourself in a framework in which you do expect that some thermodynamics can emerge. which means that you're interested in systems with many degrees of freedom and in some thermodynamic limit where you also send somehow size of your system to infinity. You have a finite densities of particles or spins. You have interactions between these degrees of freedom. And also you have, let's say, total energy of your system that is extensive, so which scales with a number of degrees of freedom. So an energy density which is not that of the ground state. You're not interested in the boundary of the many-body spectrum, but rather in regions which are in the middle. So another comment is that usually in this field, you think about systems of either fermions or hardcore bosons or spins that are maybe systems for which there is not an obvious notion of semi-classical limit because interactions are local and the Hilbert space that you have for each degrees of freedom is bounded. So in alpha, you just have two states which span your local Hilbert space and not you cannot pile up, for example, a large number of degrees of freedom on a site as you would be able to do with a boson and then take this number to infinity. And in fact, often you're interested in looking at or in characterizing really quantum correlations such as entanglement, and this is related to the lectures that you have heard before during the week. And the reason why I stress this is that nevertheless, so as Laura explained, let's say these ideas of ATH actually were born in some sense in a semi-classical setting. So this, if you want, goes back to Berry conjecture, and then these seminal papers of Srednitsky and Deutsch are essentially dealing with semi-classical systems. But nowadays you're moving away from the regime and really you're interested in systems which are not precisely semi-classical, please. Oh, I just mean, so if you think about a lattice where you have one of these spins or fermions, okay, if you think about spins for each site, you have 1 degree of freedom, and so they are the same thing. If you have particles, you can fix a density such that you have a certain filling of your lattice that is not 1, but is 1/2, but still the two scale in the same way. So the ratio between N and L is a number which is of order 1, let's say. Okay, yes. You mean for single particles? For single particle, you mean? Yes, 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 okay. Yeah, no, indeed. So I think the purpose here was to say that this is a very useful, let's say, point of view, but it's not something that you can, at least in my view, easily extend to the type of systems that you have in mind here, like spin systems, but for sure. Ah, okay, yes, okay. Thanks. Okay. So now, what are you looking for then for these systems? So obviously you want to see signature of the fact that this unitary evolution is incompatible with this scenario of thermalization. So what you ask is that you can find at least some set of initial conditions and some set of local observables, and I will go back to this in a minute, such that if you look at, so usually people look at 1-point functions in time. So you look at expectation values of these local observables on your time evolving state, which of course you can write as the trace of the observable against the density matrix, which describes your system at time t. Then what you find is that either this 1-point function, let's say, do not reach some stationary value that is what would correspond to equilibration or relaxation. So this community usually is referred to as equilibration. So equilibration would mean that if you take some large time limit, and then you also have to take some limit of, let's say, large system size of your system, then your expectation value reaches some stationary value that you can identify usually with the time average of the observable life. So whenever this is not true, then you can speak about a failure of relaxation or equilibration, which is more or less what you see in here. So the persistent oscillations that are long-lived in this type of experiments somehow hint at failure of equilibration. Now, what may also happen is that you do relax, so you do reach some stationary values of your observable, as you see in here, but you do not relax to a state that you can capture using thermodynamics. So you do not, this expectation value do not relax to the thermal expectation value that is obtained tracing the same observable against a density matrix, which is Gibbs-Boltzmann in form, so which is of the form e to the minus beta h. That is therefore just described and parameterized by this inverse temperature in here. That is a quantity that you relate to your dynamic initial condition by looking at the energy density of your initial condition. So this is unitary dynamics, so energy is preserved by time evolution. So what you can do is you compute the expectation value of your Hamiltonian in the initial condition. This gives you the energy of the system, and then you fix beta by requiring that this expectation value is equal to the average energy that, from a Boltzmann measure with that particular value. So this is an implicit equation for beta. This one. Yes, so So there are specific, let's say, models that you can cook up where you have, so I will go back to that, maybe it will be more precise, but where you do have what people call exact scars. And then if you, so exact scars will be special eigenstates of your Hamiltonian that have a given relation in terms of energies that are maybe separated by some fixed frequency. And then if you choose your initial condition in such a way that it's really a superposition over this few number of eigenstates, then you should see these oscillations which are really persistent at very large times. But you're effectively looking at time evolution of a system that is a superposition of a few number of eigenstates which have some special properties. Whether you can really realize it in an experiment and see perfect revivals, where maybe some of these, some of the experiments in here, so these are not with scars, are with bosonic systems, and they do claim that they have recurrences that they see experimentally, but okay, I should. So if you go back to this specific example, in theory, you can think about situations where the revivals be perfect in that your dynamics is really projected on a subset of eigenstates of your many-body Hamiltonian, and then you have, let's say, periodicity which shows up. I don't know if anybody has more comments. No. Yes. So I would. Yeah. I would call it. What I will call it is weak ETH violation in a minute. Okay, so before let me, so far it's a bit empty, this definition, because one has to be a bit more precise about initial conditions and what type of observables you are interested in. So just to be more precise about initial conditions, so I think that when you think about thermalization in this setting, you should ask that you have such convergences of one-point function for any possible initial condition that you can think of. Because of course, in your quantum system, at least in theory, you can cook up initial conditions, which are maybe superpositions of eigenstates at very different energies. And there you do not expect that your system would be described easily by some Boltzmann in the long time limit. You have to ask something about the initial condition. And what people usually do is to ask that the initial state is such that fluctuations in energy are sub-extensive. So if you take your Hamiltonian and you normalize it by the volume and you look at the variance of your energy in the initial state, you ask that this variance goes to 0 when the size of the system grows. So this corresponds to the fact that the energy density of your system is well defined and concentrates around some specific value. And this is what happens typically if you have states which have some sort of product structure in space. In that case, you will find that in general, this variance scales like 1 over the volume of the system. And this is what allows you, so once you have a well-defined energy density, this is what allows you to have a well-defined temperature that you expect to emerge in the large time limit. So when you look for violation, you look for violation for initial conditions of this type. And then about the observable, well, people usually require that the observables that you look at some degree of locality. So they are either what I call here strictly local, by which I mean that they act on a number of sites, let's say in your lattice, which is finite and bounded. So this is just a trivial example. Or they are local, by which one means that they are linear superpositions of this type of strictly local observable. So you have a density that you then integrate over your chain or over all your lattice. So these observables are local in the same sense as the Hamiltonian of your system is a local operator. Okay, another comment maybe, which might be useful, is about this definition of equilibration, because I think that here, when one thinks about large time limit and one asks that any, let's say, temporal fluctuation is suppressed, one has to keep in mind that there is necessarily some thermodynamic limit or large size limit to be taken there. And the reason is that if you have a finite system with this type of linear unitary dynamics, you know that you will always have these quantum revivals which occur. And therefore, whatever I wrote before, strictly speaking, for a finite system, cannot hold. So either you take this large time limit after taking the limit of large sizes, or you define some weaker notion of equilibration, which goes through time averaging, which suppresses time dependencies for finite systems. So maybe I just very shortly, sure. But two-point functions are which are not classical systems. Okay, I don't have in mind something like this, but of course, I mean, the reason why I put equilibration in brackets and I talk about relaxation is that at least classically, you know that two-point function matter and fluctuation dissipation, you want to test that to say that you are really at equilibrium. And here, instead, people usually discuss only one-point function. So maybe there are, in fact, examples, but one should check. Okay, so why revivals? Well, the idea is that if your system is finite, in general, what you expect is that there is always some time scale at which essentially your system goes arbitrarily close to the initial condition. And this you can characterize by looking at revival probability, so the overlap between the initial state and the time evolved state. And the idea is that if you ask so this quantity is equal to 1 when time is t is equal to 0, and you can be arbitrarily close, or you can ask to be arbitrarily close to 1, and you should find that there are times at which this condition is satisfied, which nevertheless you expect to scale somehow with the size of your system and to diverge when you send the size of your system to infinity. And this statement about states, of course, translates into statements about observables. So expectations of local observables in the dynamics of a finite system should somehow show such revivals. So this is just one sketchy way to write such an expectation. So you have a finite system with eigenfunctions. You can decompose this expectation value in the basis of eigenfunctions. So these C are the coefficients, so the projection of your initial condition on the eigenfunction labeled by alpha and beta. And you will have a diagonal term which is time independent, that is what you would reduce to if you take the time average of this quantity. And then you have this term which encodes all your time dependence. And if you sum over a finite number of frequencies, then this is a function that is, I think, quasi-periodic. So you can show that if you start from a given value of delta A at time 0 that is large, eventually you do find times at which this quantity is of the same order as at time t equal to 0, which is actually something that you expect for this dynamics, because unitary dynamics is time reversible. So if you look at evolution in this direction, you should see the same as if you look at evolution in the opposite direction. So this is something natural to expect. So how can you kill this delta A? So the first thing that one can think of is precisely to take this limit of large sizes, which would push these revival times to infinity, basically. And if you do this, what you are allowing is this mechanism that is quantum dephasing, that in this framework, you can rephrase as the fact that when your system size goes to infinity, you are now summing over an infinite number of terms. You are summing quantities which are oscillating with very different frequencies, and then this infinite sum, due to cancellations between these oscillations, should converge to 0, and then you kill this time dependence, and you reach convergence to this stationary value. That you can also, so here I'm just rephrasing it in Fourier space. So this delta A is just the Fourier transform of the so-called spectral function. And you know that if in the limit of large sizes, this spectral function, which is for finite systems, is a sum of delta function, if this converges to some smooth function, then this integral in here goes to 0 when you take the limit of time going to infinity. So what are possible way out to this dephasing scenario? So what I can think of are two mechanisms at this level. So the first one is that, so you want that this function does not become, let's say, a continuous, so that you don't coalesce all these deltas into some smooth densities. And one way to do this is to have particular cases in which your initial condition selects only a few number of terms in this sum. So it has a projection on a number of eigenstates which is sufficiently small so that effectively, even if you take the large size limit, this sum remains more or less finite. And this is, I think, connected to these ideas of quantum scars that I will go back in the following. And another mechanism that you can think of is that even if you take this large size limit and you still have sum over many eigenstates, there are some subtle mechanisms that make it so that this function does not become smooth, but it still remains a sum over, let's say, delta peaks, which maybe are dense, but still have some sort of discrete properties. And I think that this is connected to what you have in problems of single particle disorder systems and Anderson localization. So if you think about, let's say, eigenvalue densities for this problem, you have what mathematicians call pure point spectrum, which more or less corresponds to the fact that densities of these forms have still a discrete nature, even in the limit of large sizes of your system. You mean this and this? No, here I'm thinking, rather than thinking about, let's say, coefficients of your wave function in some basis, which in that case would be the position basis. Here I'm thinking about coefficients of your initial condition. Well, okay, in some sense, you can do the same if you choose your initial condition to be one eigenstate of position. But let's say in here, I was referring to the case in which you pick up precisely your initial condition in such a way that it has overlaps on few eigenstate, and this is, can be more general than Anderson localized case. But I agree with you that if you have Anderson localization, you start from an initial condition which is localized, and then you, in fact, will have substantial overlaps only on a few number of wave functions. So that's a good comment. Okay, so this is about large and limit. And as I was saying, another way to deal with finite size systems is to ask something weaker, which is that you equilibrate and thermalize in the sense of time averages, where you basically ask that your dynamics is such that this expectation value stays close to the stationary value for most of the times, so that the integral over time of these fluctuations is small and bounded. And this should, of course, go to 0 when you send the size of the system to infinity, which I think is more close to classical notions of equilibration. Okay, so these were just comments. And now let me go back to, let's say, the main matter here, which is, so you want to show that this equilibration and thermalization does not occur. You have unitary dynamics, so it's very natural to rephrase this in terms of conditions of eigenfunctions and spectrum of the Hamiltonian. And I will start with eigenstate structures, because of course this is what connects to Laura's and to these ideas of ETH. Okay, so this is a recap of what Laura told you. So on top, it's Landau stating ETH, maybe before anybody else, I don't know. So you see that this is volume 9, where he says at a certain point, according to the fundamental principles of statistical physics, the results of statistical averaging does not depend on whether it is with respect to exact wave function of a stationary state of a closed systems or by means of the Gibbs distribution, which is more or less what you're asking if you focus on the diagonal part of ETH, which is requiring that if you look at expectation values over eigenstates, the same eigenstates, so alpha equal to beta, this is reproduced by expectation values over the thermal measure. And then you know that there is also this off-diagonal part, which is what allows you to control fluctuations in time of the dynamics. Now, what you can show is that if you have such an ansatz, which is true for all your eigenstates, then you can argue that thermalization in the sense of time averages occurs for initial conditions which have these properties of, let's say, being a superposition of eigenstates, which are in an energy window that is not too large, but which is narrow enough so that the energy density is well defined. And this is Radnitsky. Okay, so violations. So as I was saying, you can think about two different scenarios. So let me focus for the moment on the diagonal part of the ETH ansatz. So there is this distinction that I think was introduced back in 2011 in this paper, which is a distinction about weak and strong violations of ETH. So I would say that weak violations of ETH correspond to this scenario in which you have your Hamiltonian, you look at eigenstates, and you can find a certain number of eigenstates for which this condition is not satisfied. But the fraction of these eigenstates goes to 0 when you take the limit of large sizes. So this becomes a measure 0 set of eigenstates in this thermodynamic limit. But nevertheless, if you play a bit with initial condition, it may be that you manage to pick up precisely these eigenstates, and this is what people do with these quantum scars. So this would imply that you have violations of, let's say, thermalization or relaxation for some appropriately chosen initial condition. Now, the stronger statement is that that equality up there is actually false for, let's say, most of the eigenstates of your system, and this is what would imply instead that most of the initial conditions that you choose would not equilibrate and thermalize. So I like to use this distinction just to organize then the discussion about examples. And let me also introduce clean versus disordered systems. So the strong ETH violations, so the examples that one has in mind are, on one hand, integrability for clean systems, and for disordered systems, this phenomenon of many-body localization that is, in some sense, also connected to integrability. Whereas for weak ETH, there are these several mechanisms. So quantum scars, as we mentioned, Hilbert space fragmentation, and I put here also quantum glasses, even though maybe in some cases this should be in this squaring here, but okay, we can discuss about this. So what? I don't know. Minutes. Yes. So what I'd like to start from is this case of clean integrability that is perhaps the most standard framework that one thinks of when thinking about violation of thermalization. So examples of integrable Hamiltonian, quantum integrable Hamiltonians are, I mean, there are plenty. I just wrote down in there as an example a spin chain with couplings JX, JY, JZ, which are non-random, but which can be different from each other's. And a type of Hamiltonian, which are one-dimensional, in this case with spins, are integrable and this means several things, but you can think about the fact that you can solve them in the sense that you have a way to write down parametrization of the eigenfunctions, which goes, for example, through beta ansatz, and you can build the spectrum of the full Hamiltonian in terms of single particle-like excitations of your system. And as you know, these are also systems for which you can actually build conservation laws. So you know that your dynamics has some symmetries which really constrain time evolution of your system. So symmetries means that you have operators, so this should be IN, which are conserved, meaning that they commute with the Hamiltonian. So if you start from an initial condition, which is also an eigenstate of one of these operators, so which is associated to one particular quantum number in the spectrum of the operator, you know that this quantum number will be preserved by unitary dynamics. And these operators are many, so extensively many. They are at least as many as the degrees of freedom that you have in your system. They commute with each other, and they have this peculiarity that is important of being local in their structure, which essentially means that you can decompose them as a sum overall size of your lattice of some strictly local operator which acts at the given site or in a region which is bounded in the vicinity of these sites, and then you have coefficients in the expansion that of course depend on the operator that you're looking at, which are of the order of 1. So this is precisely what you do when you write down your Hamiltonian. Now there are more general notions of locality in this community that they call quasi-locality, which refer to the fact that this density inside this sum is not bounded in its domain, but it can actually have an unbounded domain, but with a sufficiently fast decay of, let's say, of the strength of the term which are far away, but okay, let me not go into that. So the important point is that you have this idea of locality in this sense. And then if you have this, you can understand that somehow ETH does not hold, because what ETH is asking you is that if you take two many-body eigenstates which have the same energy density and you try to probe them with local observables, you will not be able to distinguish them because the expectation value of these local observables is the same, which because it is the one given by your thermal measure once you fix the energy density. But of course here this is not the case, because if you fix your energy density, you will have many eigenstates in there which differ by the value of these conserved quantities. So this can be diagonalized simultaneously with your Hamiltonian. So your eigenstates are also eigenstates of all of these operators. And the quantum number in two different eigenstates associated to this operator can be different. So if you were able to measure these operators, you will be able to distinguish between these eigenstates. So these eigenstates are not locally distinguishable, and ETH breaks down. Now, maybe you cannot measure directly these operators, but since they are local, what you expect is that when you look at local observables that you like, they will have some strong overlap with some of these conserved quantities, and therefore you see that also the expectation values of these local observables take different values depending on the eigenstates that you're looking at the same energy density. Now, can you check this explicitly? Well, people have worked a lot. There's a lot of literature. So what I'm showing in here is a plot which is taken from this very nice review paper that Laura also mentioned, I think. And this is an example for the Hamiltonian on top. So these are hardcore bosons on a one-dimensional lattice with nearest neighbor hopping interaction terms, and then next to nearest neighbor hoppings and next to nearest neighbor interaction terms. And this is an Hamiltonian which is integrable if you switch off, let's say, the third and the fourth term. So if you set J prime and V prime equal to 0, and which is not integrable if you have J prime and V prime which are not equal to 0. Now, what they do in this numerics is to diagonalize exactly this Hamiltonian. So they compute the eigenstates, and then they look at the expectation value of this momentum operator for k equal to 0. And what you see are scatter plots. So this is the spectrum, the many-body spectrum, as a function of energy density, so energy divided by length of the chain. And all the dots are let's say the value of this operator sandwiched on the eigenstates of the Hamiltonian at the given energy density. Now, the integrable case corresponds to this picture in here. And what you see is that indeed, if you fix a value of the energy density, you have a large spreading of this expectation value. And this is, let's say, a width that shows a very weak dependence on the system side. So you do not expect that to send system size to infinity, this thing will somehow narrow and give you, let's say, a well-defined line which corresponds to a one-to-one correspondence between energy density and expectation value, which is instead what you expect as soon as you lose integrability. So if you switch on this coupling instead, this should occur, and this is kind of indicated in these numerics by the fact that there is this system size dependence. You see that the curves are getting narrower as you increase the size of your system. Okay, so this you can interpret as numerical evidence of the fact that ETH is violated for these systems. In the integrable case, or you mean fluctuations? Yes. Yes, so you say exponential, but I think this is for the off-diagonal things. So I would say weaker than exponentially fast. So of course, for off-diagonal, they decay exponentially fast. This is part of ETH. But if you think in thermodynamic sense, I think that you would expect that fluctuations go down like, I don't know, 1 over some square root of volume, but I'm not sure how this translates here. Maybe there are inputs. For the diagonal matrix elements.
I think it's exponential. There is some numerics also.
Okay. Yes, it's algebraic in that case, I think. Yes. So if it's algebraic in the integrable case, it should be faster in the thermalizing case, right? Okay, thank you. Maybe one more comment on this. And so the comment is, okay, you violate ETH, but on the other hand, so these are systems for which you can actually say a lot of things. So there has been a tremendous amount of work, in particular in recent years, on these quantum integrable systems. And you kind of know, so, okay, your stationary values of observables will not be given by Gibbs-Boltzmann measures, but you know how to adjust this Gibbs-Boltzmann measure to get a stationary state. And this goes through the so-called generalized Gibbs ensemble. And the idea is that this, let's say, stationary limit that you reach, you get it as the trace of the very same operator against some generalized form of Gibbs-Boltzmann measure, where instead of putting just the Hamiltonian, you also put your conserved quantities. And each of these conserved quantities is associated to some Lagrange multiplier, which plays the same role as beta in the standard thermodynamical case. And you can think of as some effective temperature associated to the particular operator to which it is coupled. And I think that you can prove in several cases that if you have initial conditions for which fluctuations of the expectation values of these operators are subextensive, as we asked for the energy at the beginning, then you have convergence to the predictions of generalized Gibbs ensembles. And in some sense, you can also have some generalized version of ETH. So I don't know if the literature that I'm citing here is up to date. So the works that I know are given for non-interacting and translational invariant integrable systems. Maybe there is more nowadays in the literature. But the idea is that if you now, instead of fixing just, if you want, the energy shell and looking at expectation values over eigenstates which belong to the same energy shell, so which have the same energy density, you generalize this notion by fixing also densities associated to your conserved quantities, and you look at eigenstates which somehow have the same value of density of all your conserved quantities, so not just the energy, but also the other operators, then you find that local observables in these generalized shells do satisfy this condition of being locally indistinguishable. So if you take any two eigenstates that belong to this space, then the matrix elements of local observables are basically the same, at least the diagonal ones, these eigenstates. Okay, so this was about integrability, and now I think I'm late. So maybe it's time to stop. Should ask glassy people. Okay, so the way you can think about this is just that you have constraints that are given by your initial conditions. So if you have an average value of this quantity, which is encoded in the initial state, you know that this should somehow be conserved. So you have to plug it in whatever describes your stationary limit. And the Lagrange multiplier, which enforces that this average is exactly the one that you have in the initial condition, is precisely this quantity here. Now, in which sense you can interpret this as a temperature? I think you can. So this is one reference where, for example, they look at, so the question that they ask there is how can I compute and measure these Lagrange multipliers? And they use generalization of fluctuation dissipation theorem that is what you can use to measure temperature in a standard thermalizing system. And they show that somehow this coefficient control relation between correlation functions and response functions for these operators, exactly as it happens for standard temperature in equilibrium systems. So you can think of them as in an analogous way as temperature, except that you do not have fluctuations in energy, but you have fluctuations of these quantities. Yes. That's tomorrow. Because my slide is not complete. to relaxation. Yes. This, I think, or you mean finite or sub exponential? That's your question. So really finite or? Mm-hmm. Yeah, that's like. Yes, so in scars, I think the general picture is that you look at your spectrum, you have these outlier eigenstates which are separated in a regular way in energy, at least in the simplest case. And the number of those is maybe scaling algebraically with the system size, not exponentially, that is the natural scale that you have in these many body systems. So it's not finite in the sense of 3, but it's yes, still growing if you want with the, yes. Thanks.